The latest Linux security issues are a great reminder that keeping your Raspberry Pi secure is not something you want to ignore. And copy.fail is a perfect example of why Raspberry Pi security isn't just run and forget. We're going to update, verify, mitigate, improve what actually works to secure your Raspberry Pi. That being said, let's go engineer some stuff. The easiest first step we can take is to update our Raspberry Pi. Before updating, our Pi is running Raspberry Pi OS Trixie 13.3 with kernel version 6.12.62. To update, we'll run sudo apt update, followed by sudo apt full upgrade. Then we'll give the Pi a reboot, and after the update, we're now on Trixie 13.4 with kernel version 6.12.75. So awesome. Problem solved, right? Well, not quite. Even though we did get a newer kernel, the Pi is still vulnerable to copy.fail. And this is an important security lesson. Updates are the right first step, but they are not magic. Not every Raspberry Pi OS update includes every upstream Linux kernel patch right away. So before assuming we're safe, we need to verify what actually changed. In this case, we can check not only the Raspberry Pi OS release notes, but also the kernel change log, and then search for the CVE, our patch related to copy.fail. And as it turns out, this kernel update does not include the fix we need. So are we just out of luck? Of course not. At this point, we have two options. Compile a Raspberry Pi kernel with upstream fix, or apply a mitigation while we wait for the official package update from Raspberry Pi OS. We'll start with the more involved path, compiling the kernel ourselves. You don't have to do this, but it's a great way to understand what your options are when updates haven't caught up yet. To get the kernel source code, we're going to use Git. It should be installed by default, but if not, it's easy to get. Then we'll clone the Raspberry Pi Linux kernel source. I'm using --depth equals 1 here so that we only pull down the latest version of the active branch, because otherwise this download can take a wicked long time with the full tree history. Next, we'll install the build dependencies we need to actually compile the kernel. One nice thing about building from source is that we can also verify whether the source tree includes the fix we care about before we spend time compiling anything. Because this is a Raspberry Pi 5 running a 64-bit OS, we'll start with BCM 72712 defconfig. Then we'll set a custom local version. You could set this to whatever you want, but in my case, I'm going to use -sjr. And this does two useful things. First, it keeps our custom kernel modules separate from the stock kernel modules. And second, it makes it really obvious that when we're running our custom kernel, because that suffix will show up in uname. After that, make old defconfig. Make sure the kernel config is complete using the defaults from the current configuration on a Raspberry Pi without forcing us to go through a giant menu of kernel options that we really don't need to focus on right now. And we can quickly confirm that our local version was added. Now we can start the actual kernel build. We're compiling the kernel image, the kernel modules, and the device tree blobs. If you want a deeper explanation of what those are, let me know and I'll absolutely be happy to do a future video on that. On the Raspberry Pi 5, this build took about 20 minutes, but thanks to editing magic, we do not have to sit here and watch the whole thing. Once the build is done, the first thing we'll install is the kernel modules. This usually takes a minute or two in real time, not edited fast forward time. Then we'll copy the kernel image into the firmware directory using a custom file name. And this is important because we are not overwriting the stock Raspberry Pi kernel. If something goes wrong, we still have a clean fallback. Before changing the boot configuration, it's always a good idea to back it up. Then these commands tell the Pi to boot our custom kernel on the next restart instead of the stock kernel. A quick cat confirms the custom kernel line was added, and now we are ready to run sync and reboot. After the reboot, both the full forms of uname confirm that our custom kernel is running, and we can see the sjr suffix and our build date. Now when we run the copy.fail exploit, we no longer get an automatic root shell. Instead, we're prompted for a password and only gain root level privileges through normal authentication, not through the vulnerability. But there are plenty of times where a patch is not available yet or can't be applied right away, and that's where mitigation comes into play. Thankfully, copy.fail includes a very clear mitigation we can apply to our Raspberry Pi when we look at their website. And keep in mind, this was filmed before upgrading to our custom kernel, so at this point, the Pi is still vulnerable. By running these two commands as root, we disable the algif ahead module, which is the main kernel module involved in this vulnerability. And now, when we rerun the copy.fail exploit, it fails because the module it needs is no longer available to attack. And this is exactly what we want to see, a simple mitigation that reduces the attack surface and protects the system while we wait for a proper patch for the Raspberry Pi OS. Now let's be real about security in the Raspberry Pi. New vulnerabilities are popping up every day, and it can feel like a giant game of security whack-a-mole. Would you leave your front door unlocked all the time? Of course not. Would you ride a bike without a helmet? Hopefully not. Would you eat that delicious piece of pie that's been sitting in your fridge for a month? Tempting, but still probably not a great idea. And a lot of security comes down to the same kind of common sense. Keep your Pi updated, reduce your attack surface, and don't blindly run commands from the internet that are random or you don't know what they do. And try to understand what your system is actually doing. If there are other security topics you'd like to see me cover, or you just have any questions in general, please leave them down below. I'm always happy to answer them. And if you found this video helpful, please don't forget to like and subscribe. And as always, I'm Sam the Engineering Man, and I'll see you all in the next one.